Hey guys, so we are talking about gas mixtures, and there's something that is going to be helpful for us, especially when we're thinking about our lab, and it's using an application of Dalton's law of partial pressures. So we're talking about gas mixtures, right? When we're talking about partial pressures, we're talking about the fact that there's more than one gas in our container. Okay, so whenever you have a liquid, there is always some vapor above the surface, some vapor of that liquid. So if you are around water, there's always going to be some water in the air because for the fact that there is a liquid surface there. And what that has to do with is some of the liquid particles have gained enough energy to overcome the forces that are holding it as a liquid, and it turns into the gas particle. When you give enough energy for all of the particles to overcome those forces, that's known as boiling. But this, when you get some liquid, there's evaporation. So thinking about like a puddle of water in the bathroom will evaporate. You never see bubbles coming from the bottom because not all the particles have enough energy, but you get it at the surface happening. And then those gases, those vapor particles tend to stay, especially if it's in a container, will stay above that liquid if they can't escape. Okay, so when we're in lab, we talked about this when we were dealing with our lighter, finding the molar mass of the gas in the lighter. The only way to quantitatively, right, actually get a way to measure the amount of gas we had in the container in our graduated cylinder was to fill it with water first, and then get the gas in there, and then we can say, okay, there was no air bubbles to start, so the gas that's in that container is only the gas from the lighter. Well, because we collect gas over water, right, we are getting, this is a little bit different setup because this is a reaction happening, but imagine we have the lighter down where the tube is in the collecting jar. Now because there's liquid in the container, right, all liquids have some vapor above the surface. So in that container, yes, there is the gas from our lighter or the reaction that's running, but there's also a little bit of water in there, right, for the fact that all liquids will have some vapor above the surface. So in that collection flask, there's whatever gas is being produced and water vapor. So in the only way to quantitatively collect our gas, there's always going to be some water. And that's why when we refer to the gas that's being collected, it's referred to as wet gas. Even though, when we think of wet, we think that we can visibly see it, but even in gas senses, it's wet because there is some water with it. So what we need to do, especially for our lab, because all that we're talking about with partial pressures, if you're saying that all of the pressure is due to the amount of the lighter, of the gas in the gas from the lighter, well, you're actually overestimating the amount of moles because not all of that pressure is coming from the lighter. Some of that pressure is coming from the water. So what we need to do is we need to find the pressure of just the dry gas. Okay, and this is a application of Dalton's law of partial pressure because the total pressure is equal to the sum of the partial pressures that are in our mixture. And the cool thing, you're like, oh my, how am I even going to be able to figure out the pressure of water vapor, right? Because I don't know the volume that's going on. There's a lot going on. So what's interesting is the vapor pressure of water is dependent only on temperature. That is the hotter it is, the more vapor pressure there is, and there's an actual relationship, and it's been documented enough that we have a table like this that no matter how big your surface is, you could talk about a lake, you can be talking about the ocean, you can be talking about a small little glass of water that has a cap over it. The only thing that matters for the pressure of the water vapor above it is the temperature. Okay, so you can see as temperature increases, so does the vapor pressure. And it's not necessarily linear, but it definitely does have a positive correlation. As temperature increases, the pressure increases as well. And if you see at 100 degrees Celsius, which we know is the boiling point of water, the pressure, right, the vapor pressure of water is 760, which happens to be the pressure, the atmospheric pressure at sea level. So The reason why water boils at 100 degrees is because that is when the vapor pressure is equal to the atmospheric pressure, and that's the definition of boiling, when your vapor pressure equals atmospheric pressure. So if you've ever gone to Denver, water boils at a lower temperature because you're in higher elevation, you're a mile above sea level, so there's less gas up there, so there's less pressure. So the atmospheric pressure in Denver is around 633.9 millimeters of mercury. So that's why water will boil at a lower temperature. And it actually takes longer to cook food because your food isn't getting as hot because you're bound by the temperature of the water. So you have, and that's why you have different directions when you're at elevation. And then pressure cooking, if you have a pressure cooker, it actually allows the pressure to get higher, therefore increases the boiling point of water, and it will allow you to cook food faster because it's getting to a higher temperature, especially when you have liquids around. So that's why it's important that you put liquid in a Instant Pot or pressure cooker if your parents do that. Anyway, so when you're collecting gas over water, all you need to know is the temperature in order to figure out the partial pressure of that water, of the water vapor. So we're going to go here, and we're going to do this problem. Okay, it says a reaction is run and the gas produced is collected over water. So when you see this word, they would have to tell you, but we'd assume the only way to quantitatively collect gas is to do it over water. So this means we're going to have the total pressure is going to be equal to the pressure of the gas that you're interested in plus the partial pressure of the water vapor, right? That's what that means, because if you have water, you have vapor pressure. So they tell us we had a volume of 10 milliliters. They tell us the conditions in the lab, and it says how many moles of gas were produced. So when you're talking about the pressure in the lab, this is referring to the total pressure of your mixture. Okay, so we're given this piece of information, and we're interested in how many moles of gas were produced, right, from our reaction. So we're interested in the pressure of the gas times volume is equal to moles of gas times RT. So I don't want to use this total pressure because then that would be taking into account both the moles of the gas and the moles of the water. And since this, it's a byproduct that we have water in there and it didn't come from the reaction, then I want to get that out of, I can't put that into this equation because I'm just interested in the gas, okay? So in order to find this, we see that the reaction happened at 25 degrees Celsius, so we just have to look at a table to figure out what the partial pressure of the water vapor is, and in this case it's 23.8 millimeters of mercury. Remember, torrs and millimeters of mercury are essentially the same unit, right? 760 torr equals 760 millimeters of mercury. So first thing we have to do here is find pressure of the gas. So 745 torr is equal to P gas plus, and we said 23.8. And again, right, millimeters of mercury, same unit as torr, so I can just do that interchangeably. So the pressure is the total minus the vapor pressure of the water. P gas is equal to 721.2 torr. And again, like, why do we have to do this? Well, if we're interested in the moles of just the gas, I cannot use the 745 because that pressure is made up of not only the gas that you created, but also the water vapor. And if you were to use 745 in your calculation in PV equals nRT, then you would be overestimating your amount of moles. And when you have the wrong amount of moles, then things, you start to underestimate things, overestimate things. So that was our first step. Second step, we're going to now solve our equation for N gas. And the pressure of the gas, right, 721.2 divided by 760. Volume is 10 milliliters or 0.01 liters. We're going to divide by R, divide by 25 plus 273.15. And that's going to be equal to N gas. Okay. So, oopsies, 721.2 divided by So I'm just putting this into the calculator now. 0.01. Okay, I get, it's a pretty small answer. That's fine by me. You don't get a lot of gas, right? That's a very small volume of gas. 3, how many sig figs are we going for? Remember, this temperature has 3 sig figs because we're going to add 273.15. So that turns it into having 3 sig figs, so 0.000388 moles of gas. Right, so a small volume tends to have a small amount of gas. So again, just recapping, like why does this seem to be complicated? Well, we technically, when you collect gas over water, you technically have a gas mixture. And when we're talking about mixtures, we're talking, if you want to know just the moles of the gas and not the total moles in there, then you need to be talking about the partial pressure of just the gas. And we have an easy way to find the partial pressure of water. All you got to know is the temperature. So this is going to come into play in your lab because we collected gas over water, and whatever the pressure was that day in Cambridge, that's the total pressure. And it's going to be your job to, based on the temperature, figure out what the partial pressure of the water vapor was, which would be the partial pressure of H2O, and then you have to subtract that from the total pressure to get that pressure of gas. Now, this table right here goes up into increments of 5. If you Google vapor pressure of water table, you'll get ones that go to the 1 decimal place, and you should do that because you technically have that data, and you shouldn't be, say your temperature was 23, you shouldn't be going to either 20 or 25. You should be getting data for the temperature that you had. So do a Google search for the vapor pressure of water table to